Verification Corner!
Hello, my name is Rustan Leino. Welcome to Verification Corner. For millennia, mathematicians have written various kinds of proofs. These proofs can have a lot of detail in them, or some have a lot less detail, depending on how confident a mathematician feels about writing down the details. In this episode, we're going to see how you can do similar things with the computer system. You can provide a lot of details in the proof, or you can skip details and let the computer fill in what's missing. We're also going to take a look at how you can write a proof by hand and then transcribe the same thing on the computer, or how you can use the computer in the first place to develop the proof and give you hints for how to take the next step. I'm Rustan Leino.
And I'm Sophia Drossopoulou.
Sophia, you're a professor at Imperial College in London. What do you do there?
So I do research in programming languages, object-oriented programming, program verification, and I teach an advanced course on object-oriented programming and also an undergraduate course on program verification.
That sounds very nice. And now you've been visiting Microsoft Research for a while. How come?
Indeed, I have been here for 7 weeks visiting Judith Bishop from Microsoft Research Connections, and I have worked on developing material that would help me use Daphne to support my course on program verification.
That sounds very nice. Yeah, Daphne has some new features in that space that we're going to take a look at.
Yes, I have been very glad to use the new features. They are going to help me make a much better course than I had. Yes.
Excellent. So what example would you like us to look at?
Let's think. Perhaps trees.
Okay. Trees are good in computer science.
Flattening trees. Yes.
All right.
Let's have a look.
Let's look at some trees in Daphne. Here I have two data type declarations, and so they are inductive data types like you might find in ML and other functional languages. The tree, which takes a type parameter t, and it says that it's a tree of those things, whatever that t is. So a tree can be either leaf, so leaf contains something of type t, or it can be a node. So node is like an internal node in the tree, and it has a left subtree and a right subtree. So the flatten operation would then convert a tree into a sequence of codes. So a code is one of these, is also parameterized by type. So a code is either indicating something that came from a leaf, we'll call that LF, just to remind us that it was a leaf. And the other code that we can have is one that we'll just call ND, which just is some indication of an internal node. So we'll see how we bind these together with an operation. So how are we going to do that?
Well, we'll need a function, let's call it flatten.
Okay.
And it will, as you said, it will take a tree and create a sequence of such codes. If the tree is just a leaf, then it's straightforward. We'll just make a little sequence that contains the constructor LF and the contents of the leaf. And if it is a node with two subtrees, then we can flatten the first subtree, then the second, and then append the indication ND that we have just read a node.
Okay, that's all good. But maybe we could show how how the flatten operation works visually.
Have you got the board? Could you go on the board and draw something?
Let's do that. What have you drawn over here, Sophia? You were going to show me the definition of flatten.
Right. So first of all, there is a tree here. You see there is a node and it has got two subtrees, and this one has got two leaves, and so on and so on. And we see that this tree contains the word Daphne by coincidence.
Yes.
And now, in order to understand how flatten works, I have already written the result of flattening, but I would like to go through how it works on this tree. So if I want to flatten this whole tree, what we need to do is flatten this bit, which will correspond to this bit over there, flatten this subtree, which will correspond to or we'll create this sequence over here and then append the node constructor. And now if we flatten that part, then it is a matter of flattening this and this, which will give me those bits and append a node. And each of them is encoded through a leaf containing D and A. And similarly here, flattening this tree is flattening that part, followed by this bit here, and append ND, and so on. So this is the structure of how flattening will go through the tree and will create this sequence over here. And the parentheses show which bits from which trees correspond to which sequences.
Aha, very nice. Now I can see it. And parenthetically, there are a lot of parentheses. Actually, the append operation on sequences, isn't it actually associative? Could we not just get rid of the parentheses?
Yeah, it is associative, of course, and when we think about it, we think without the parentheses. But how is append defined as the append operator defined in Daphne? Is it left associative, right associative? What is it?
In fact, in Daphne, it is left associative. But if you want to, you can prove that it is associative so that it doesn't matter. But the operator is left associative.
Okay, so in our head, we can still think without the parentheses.
That's good, right. Okay, should we try to prove something about these trees?
That's a good idea. What could we prove?
We could prove maybe that if we have some measure of size, that the representation that we're getting here in the encoding has the same size as the size of the tree.
Yeah, that's a good sanity condition. So I propose that we write this proof by hand, and then we encode the proof in Daphne.
Excellent, let's do that.
Right, so what we wanted to prove is that the size of the tree is the same with the length of the encoding of the tree through flattening. And we have written the lemma over here. And I'm going to go briefly through how we can prove this lemma by structural induction on the tree. In the black part, I have written the structure of the proof. Namely, there is a base case and an inductive step. In the base case, we need to show that the lemma holds for the case where the tree is just a leaf. And here I have written what we need to show. And in the inductive step, we will take arbitrary trees T1 and T2. In the hypothesis, we assume that the property holds for T1 and that it holds for T2. And what we have to show is that the property holds for a tree that consists of these two subtrees. And in green, I have written how the proof goes. So the proof for the base case, I did not write it down. And I have written the proof for the inductive step. The proof for the inductive step starts with the left-hand side, applies various definitions, and then reaches the right-hand side. So just for indication, we start with looking at the size of a node that contains trees T1 and T2. The first thing that we can do is we apply the definition of size, and we get to this term. And now we are in a very happy position. We can apply the inductive hypothesis. So by applying the inductive hypothesis on T1, we can rewrite size T1 to be the length of flattening T1. And on T2, we obtain that the size of T2 is the length of flattening T2.
Just like you have up here, right? Okay, good.
Exactly. Right, so then we continue in that vein. For instance, here we know that the length of a singleton list is 1. So we replace 1 by the length of the singleton list. Now we push the length to the whole of the sequence, and then we apply the definition of node, and then we have reached our aim.
Do you think we can do this on the computer?
I hope so.
All right, let me go back to the computer and let's try it.
Right, okay, let's do that. So here is our proof, and now I would like to have a look at how we can do the same proof in Daphne. First of all, that's our lemma. How do we express that lemma in Daphne?
Okay, so a lemma like that is going to be expressed in Daphne as a ghost method. You can just think of, for our purposes here, the ghost method states the same thing as lemma. And I will give it a name. I'll call it size lemma. and I will parameterize it with, just like you have universally quantified over t over there, I will just parameterize the lemma with a tree t. The statement of the lemma, the conclusion of it here, is going to be written as a postcondition of the method, which we introduce as usual in program verification here with an ensures keyword. So I will just say ensures that the size of t is equal to the size of the flatten of t. So that's the statement of our lemma.
Right, so we have got the statement but not the proof, yeah?
Right.
The proof goes by induction on t. How do we express that in Daphne?
Okay, so first of all, to do the proof at all, I will introduce a body for the method, just like we would if we were writing some code for another kind of method. And to get the case study that the induction gives us here, I will introduce a match statement. I will match on t, and there will be two cases. One case is the leaf case, and the other case is the node case. So I will just type those in, and now all we need to do is for each of these two cases fill in the proof.
So if we look at the proof of the inductive step of the node case, we see that we have gone step by step, and we have started with the left-hand side, reworked it until we reached the right-hand side.
Mm-hmm.
And that's a nice readable proof. Can we do this kind of proofs in Daphne?
Yes, in fact, Daphne has a statement, a calculation statement, which does exactly this sort of thing. Let me show you. So I will start a calc statement, and in the calc statement we will have a number of lines that will be connected by equalities. So let me start by doing the first and the last line of your calculation over there. So we start by the size of the node of t1, t2, which is what we have in this case. And I will say that that is equal to, as we will prove, equal to the flatten of the node of the size of the flatten of the node of t1, t2. So that's the beginning of the calculation. But now we'd like to fill in some more steps in between.
Great. So in the first step, we just expand the definition of size and get those three subterms.
Okay.
Can you do the same?
Yep, let me do the same. So I will introduce, and I will say that the first line is equal to, and I'm about to type the other expression. And just like you have in the right margin written a hint as to what was going on in that step, I will write just a comment in the program text, which is the definition of size. So we remember what it is that we're doing in this step. And now I can type the formula, which is 1 plus the size of t1 plus the size of t2. Okay.
Great. So now we apply the inductive hypothesis as we saw earlier. What does that look like in Daphne?
The inductive hypothesis. That's an interesting one, because the way that we're going to get the inductive hypothesis in the program verifier is that we're going to, in this program setting, just simply make a recursive call to the method. So I will write another step, and in this step, instead of just giving a comment in the code, I will introduce a code block, which we, as we often do, just introduce with some curly braces, and I will call the method recursively. So I will call sized lemma, I will call it on t1, and I will also call it on t2. And those two will now give us 1 plus. And now the first application of the size lemma tells us that the size of t1, which we get from the postcondition, the size of t1 is the size of the flatten of that same tree. Size of flatten of t1. And then same thing for the other one, the size of t2 here. And by the size lemma applied to t2, we get the size of flatten of t2. So that's the induction hypothesis applied to both t1 and t2.
Right. So now we replace 1 by the length of a sequence that has got only one element, nd.
Mm-hmm. Okay. So I will say that that is equal to, and I can give the same little hint there, which will be just a singleton sequence. And so I will replace in fact, I will copy this entire line. Let me do it this way. Copy the entire line, and then I replace the one by the the size of the singleton sequence ND, which is equal to 1. Okay?
And now by the definition of the length of the sequence, we can push all the length symbols outside the term and obtain that term.
Excellent. Let me do the same thing here. And in fact, I will just do a little copy and paste down here again. And get rid of those symbols in between. So now it's the size of the concatenation of those three things. Okay.
And the concatenation of those three things is nothing else than flattening the node that contains these two subtrees by definition of flattening. So apply the definition of flattening, we get that term, which was our aim anyway.
Excellent. So I'll just write that in here. Definition of flatten, and there we are. Okay, so that is the proof term, the proof, the calculation that proves that the lemma holds. In other words, in the program context of the program verifier, it proves that that postcondition holds.
So that's great. We have got a proof written in Daphne that reflects all the thinking steps that we went through when we developed our handwritten proof. And moreover, Daphne has checked that all these steps are valid and that the proof is correct.
Mm-hmm. Now, this is wonderful. There are many details in this proof. One can see for each step what's going on. But sometimes mathematicians just get so used to doing all of the small steps that they would omit steps. How would you do something like that?
Indeed. So if I am confident about what I'm doing, I will not write all these steps, and I will just write another proof here where I will say just by induction over the tree T. Can we do such a thing in Daphne?
Okay, so in fact, let me use then the same proof structure, but let me erase some of the lines that we wrote. So I will not have any in the two cases. I will just erase the contents in between, and we hope that Daphne can also see the same proof structure. So here we just have the match with the two cases, and the induction is handled automatically by Daphne, and it proves it just as well.
That's great. So I can be lazy, and I can get Daphne to do the work for me. However, other mathematicians who are even more confident would write a proof and would just say, this trivially holds, and will do no work, or will want us think that they have done all the work and have not written it down. Can Daphne help me in such a case?
I like your challenge, Sophia. Let's erase the rest of the proof as well and see what happens. So in this case, we just have the curly braces, and indeed, Daphne proves that as well, as we could see by the little purple bar going away in the left margin. So in fact, Daphne can do the same trivial proof in this case, and that is, Daphne also thinks that it's a trivial proof, and all you need to supply are the curly braces of the proof.
That's great news.
Very nice.
Good.
Can we do something else to show this in the context of programs?
Yeah, let's do something else. And now what I would like us to do is, rather than we have already developed all the proof and we map it to Daphne, maybe we can get Daphne to help us find the proof.
Great. Let's try that.
Let's do that.
All right. So what program are we going to write?
Once we have flattened the tree, maybe we can reconstruct it. Let's write a raise function that will take a flattened tree and try to reconstruct it.
Out of coincidence, I happen to have such a function right here.
What a lucky coincidence.
Right. Here's a raise function, and it calls raise1. What does this actually do?
Right. So the raise1 function takes the top element in the code sequence and is also holding an accumulator of intermediate trees that it has created so far. And what it does is it takes this top element, the code, and if it happens to be an ND, an indication that there is a node, then it pops the top two elements out of the accumulator and puts them under a node and makes an intermediate tree.
That sounds very impressive, but I don't understand the thing. Can't we just prove it instead?
prove it. Of course, wonderful. Let's do that.
All
So,
right.
what do we want to prove?
Well, if you say that raise does the undoes a flatten, how about we show that flattening after doing that raising after a flatten gives us back what we started with?
Exactly. So, can you write the theorem, please?
Okay. So again, it will be a ghost method. I will call it theorem this time, and we will start with a tree. And I will give as the post condition the thing we're going to prove. I will say that the raise of the flatten of t, and I have to pass in that accumulator parameter, which will start off just the empty sequence, that will give us back the sequence consisting of just that one tree t. That's what we'd like to prove.
Yes, that's the property that we want. Yeah. Shall we be optimistic and see whether Daphne can do it on its own?
Seems good. It did so well before, so let me just apply the curly braces, and surely it will prove it.
No.
Not quite.
It requires some help.
Okay.
Yeah, right.
So what do we do now?
Shall we do case analysis again? Maybe we can do it by induction as we did earlier.
All right, good. Let me introduce the case analysis. So I will use the match statement as we had done before as well. So I will match on T, and we will have, again, two cases, the leaf and the node. And here we can see the underline, Daphne is complaining about the second case. So apparently it proved the first case by itself, but we need to fill in more of the proof to help it more along for the node case, that is the induction step. What are we going to do here?
Maybe we can apply the definitions of raise and flatten.
Okay.
In order to reword the left-hand side.
All right. Let me then start with the calculation. So the calculation, we're going to put in the steps. So I will start with the left-hand side of what we're trying to prove, which is the raise of flatten, and of the node of the tree t. And we'd like to prove that this is equal to the t. And now we'd like to apply the definition of...
So first of all, the fact that t we know is node t1, t2.
Should I do that I can do that in a separate step here.
Yeah.
So raise of flatten of node of t1, t2. Because the node of t1, t2, we know that's just the same thing as the t. Okay, one more parenthesis.
Right, so now we can apply the definition of flatten.
Right, I put that in the wrong place. That's where it's going to be. Okay, now the definition of flatten, say. So, definition of flatten. Okay, what does the formula become then? Well,
it is raise flatten t1 concatenated with flatten t2 concatenated with nd.
Okay, so raise of flatten of t1
plus flatten of t2 plus nd, the sequence that contains nd. Okay, and then we have got the empty sequence of trees, the empty accumulator.
Right. So what we applied was that the definition of flatten applied to such a node is the same thing as the flattening of these things, just like we saw on the board earlier as well.
Right, so it seems that the first two steps go through, but the last step doesn't. So,
that's right. So
we need to do some more.
Okay, so what could we do next?
Well, we have not applied the inductive hypothesis yet, so could we apply it?
That seems good. Let's try to apply the induction hypothesis. And the way we typically do that is we write then in curly braces, we're going to write a call to the theorem. And here I will write the theorem on T1 because we have flatten of T1 and I'm hoping that that will do the trick. But apparently...
you have to take off this extra.
I need to write what that becomes. So what does this become? Well, this doesn't quite seem to fit what we have, does it? Here we have raise of flatten of something that starts the same way as we have up here, but here there's nothing else, and here it continues with other stuff. It doesn't seem like I can complete this, really.
Well, so it seems like our theorem is actually too specific and not strong enough to be proven by induction.
Aha.
So
Do we have to do that thing that's called strengthen the induction hypothesis or generalize
yes,
it?
Generalize the theorem. So let's have a look how we can how we have to generalize it.
Okay.
So when we look at this structure here, we see that we need to be able to talk about what happens when we have a flattening of a tree followed by some more codes. So this would be one way of generalizing.
Okay.
And moreover, here we are requiring that the accumulator is empty, but there's no reason to require that the accumulator should be empty.
Could be anything.
Yeah.
Okay. So maybe if we write a lemma that has that generalization that you're now hoping for.
Right. Okay. So perhaps you can start by writing it and to
Okay.
improve it.
In fact, might it look just like that?
Ah.
Here we
so
have.
what does it say?
So instead of the theorem, which took just a tree as a parameter, this lemma takes a tree parameter, and it has the extra stuff that you were asking for. We're calling that CDS, just as another
Yeah.
sequence,
And the extra accumulator, the non-empty accumulator.
which is just called TS, and it could be
right.
anything. It doesn't have to be empty.
So now the question is, what is that equal to?
And so here, this lemma says that if we have something of that more general structure, it will be the raise of that sequence. In other words, it sort of consumes this part, and instead where the theorem took the t and put it over here on the right in a sequence, here we're going to get the same t be prepended to the extra stuff that we have in the accumulator.
So I think that's wonderful, because this lemma now expresses exactly the reason for which raise is working. It says that it takes the top of if there's a flattened tree at the beginning of the codes, then this flattened tree gets pushed onto the accumulator, and then it continues with the rest of the codes. It shows how the function is working.
Excellent. This lemma helps me understand the code a little here now. So,
Great.
okay,
and Daphne helped us find it.
So now there are two things that we should do when we have such a lemma. We should use the lemma, and we should prove the lemma. Which one should we do first?
So I propose that we first use the lemma in order to prove the theorem, because I think that I have a hunch it should be easier to do that. And moreover, if the lemma does not help us do the theorem, then we don't need to bother with the lemma.
Excellent.
So let's go for the theorem.
Okay. So now I had started writing this proof over here. Do we really need this stuff? Should I?
I think we can throw it all away and
Let's
apply
throw it away.
our
Okay, should I throw it all away, perhaps? So if we apply the lemma in here instead. So what I'd like to do now to fit the thing into the lemma is I'll pass the same tree, and there was no stuff sitting after it here, so that was just the empty sequence. And then the last parameter that we allow to be anything is in fact the empty sequence here, so I will just pass in the empty sequence here as well. So calling that lemma, then what we get on the other side, if I just read it off from the lemma, is the raise of the empty sequence, and then with a tree followed by the empty sequence.
Yep.
Good. Okay. Now we're getting a complaint. It says this calculation step might not hold. What's going on?
Oh, let's have a look.
It seems to me that
So let's have a look again at the lemma. The lemma says that flattening of a tree followed concatenated with codes.
So it seems.
And so it requires, in order to be applicable, it requires the rays to be applied to flattening of something plus empty.
Aha.
But if we look at what we have here,
We don't have the right form.
we don't have the right form.
We actually needed to introduce here first something that concatenates to that the empty.
Right, so why don't you add the plus empty there?
Okay, right, I'll do
No, you
another
can add it in there.
I could add it there, that's true.
Yeah.
Let's add it here. Plus empty. Okay,
Right.
now it proved that step.
Oh, wonderful.
But
And
it's
what
not-
I really, really like is the fact that we're allowed to apply the lemma without having proven it.
Aha,
So
excellent.
it's kind of a hypothesis that we made. We see whether the hypothesis helps us get to our goal, and then we can decide whether we are going to work on the hypothesis. So that's a great strength of the tool.
Wonderful. But we're not quite done yet. It complains about the postcondition. Apparently this calculation that we set out to do is not quite matching what we have up here. And it seems to me that it doesn't match it quite just because of the thing that we introduced.
Right.
How would
yes.
we get rid of that? In fact, isn't it always the case that the flatten is indeed, that the sequence that you concatenate the empty sequence to, that's just the same thing. It's the right identity of concatenation.
Right. So perhaps we just need to remind Daphne of that fact.
Okay, let's do that. So I will copy this line pretty much, but I'll get rid of that part again, and I will write a hint in between that now I'm going to just assert in the hint that flatten of t is in fact the same thing as flatten of t plus the empty sequence. That is, as you said, we're asking Daphne to prove this and then apply it in the step, and that has now worked.
Oh, great. So we have finished with the proof of the theorem.
Excellent, but we do have the lemma left. So
Okay.
let's continue with that.
Let's continue with the lemma.
Okay, so let's start optimistically first with just introducing the braces to see what happens. No, we need to do more things. Okay, so what are we going to do here?
Start with the case analysis.
Okay, that seems to be a good thing, as usual. Okay, that is the case analysis.
Right. So we need to do some work on the case of node, and let's do some calculations again.
Excellent. Okay. Is it all right if I fill in the first and
Yes,
last step
please.
here? So in fact, let me just copy it from up here. This thing equal to, oops, I didn't quite get all the characters. There we go. Okay, that's what we'd like to do. If we can close the gap in that calculation, then we're all fine.
So I think as a first step, we will need to apply the definition of flatten and the knowledge that T is a node.
Okay. All right, so definition of flatten. So then I will get rays, and again, this flatten, just as we had when we started to do the proof of the theorem, we will get flatten of T1 plus flatten of T2 plus the
ND.
singleton ND. And this all thing plus the CDS that we already had and the TD. So we replaced the flatten of T with this definition here, and we got that. Okay? What's next?
So now it seems to me that we should be able to apply the inductive hypothesis. We have something of the form flatten T1, blah, 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 blah. So we should be able to put the T1, push it to the accumulator.
Okay, good. So I will call the lemma recursively here, which is the induction hypothesis. For the first part, T1 up here is just going to be, T is going to be T1. The other one is going to be this whole sequence of things that we have. And the third part is just going to be the TS that's sitting as the last parameter. And if we successfully apply that, then what we will get on the other side after applying the induction hypothesis is the CDS, which is this parameter, followed by the singleton of that tree, T1, plus
T's.
the T's.
Yeah,
Okay.
I'm convinced.
You're convinced.
Oh,
But we
Daphne's
get an error.
not.
What's going wrong?
So Are we sure that the form that we have above the lemma is what Daphne expects? So this bit here.
I see. So in Daphne, the concatenation, sequence concatenation is left associative. And what we need is we need to break it up differently. So we can do something a little bit similar to what we did before as the hint. We will remind Daphne of this. So let me introduce another step. And in that step, I will just simply assert that what we have here, even though it's written as the concatenation of 4 things, that is equal to almost the same thing, but I will parenthesize it differently.
Make sure that the parenthesis is the way we need it.
I copied the wrong thing here. Copy that thing. And the parentheses I will insert in this way. So again, now Daphne will prove that this assertion is correct, and then it will be able to use that in the step. Let's see, what do we have?
Yes, but we need to write what it leads us to. We
that's
have
right.
missed the intermediate step.
Indeed, that's what's missing. So I will write this formula, copy it almost as we have it, but I will insert the parentheses. Okay, there we go. Wonderful. So what happened was it proved that step, and now it allows us
and it applied the inductive hypothesis and allowed us to make progress, but we still are not done.
That's right. But now we can see more readily that we can apply the induction hypothesis again here soon, because we start with rays of flatten of something. But learning from what we just did up here, it seems that we need to glump these things together to reassociate them before we can actually apply it. I suggest we do that right away.
Okay.
With an assert.
Can you put those two together? Can you put the assertion and the call of the inductive hypothesis together?
I could. I can write them both in one hint, or we can write them in 2 hints, whichever we prefer. Oops, I do need one more term. So this thing is equal to, and I will copy it but parenthesize it differently. So put the parentheses here. Now I'm writing it in one step. We can apply maybe it's a little bit easier to see if we do it in 2 steps.
Yep.
I will introduce the parentheses here. And now we are ready then for the induction hypothesis. Let me just see. The purple went away in the margin. So Daphne is happy with that. And here I apply the lemma to T2, and then this part. Oops, too many parentheses. And then followed by this entire thing. Okay, we're getting close here. So let me fill in what that will give us. So from the inductive hypothesis, we now have that this is the rays of, and it's going to be simply this parameter, and just like that. And then on the other side, it will be T2 plus those things that we had over here.
Yeah.
And let me be careful.
Those will be bracketed together.
That's right. So let's do that right away. Just like that.
Yeah.
Okay, let's see where we are. So we can see everything that we've done up until that point, Daphne is also happy with. We're not quite there yet. So what are we going to do now? Maybe...
So if you look at what we have in our current term, we have the case where the raise function takes, pops the node out of the codes and takes the 2 top trees out of the accumulator. But still, Daphne is not happy. So perhaps it is another case of we need to tell Daphne that the concatenation is associative, and therefore it will be able to see that we can pop T2 and T1 out of the accumulator.
Good. Let's give that a shot. So I assert here that the concatenation of these 3 things gives us the same thing if we had concatenated it in the other order. Like that. And if that's the case, the formula that we get on the other side will be the same thing, but without these parentheses, like that. And Daphne is now happy with that and completes the proof. So in fact, now we have the entire proof. And
Wonderful.
So what we have proven now then is the theorem, which shows that if we raise after flatten, we get back to where we started. In other words, we've proven the correctness of that encoding and decoding sequence.
And we have not we didn't have a plan for our proof to start with. We just were developing with Daphne, and as we went along, we discovered what necessary intermediate steps we had to satisfy.
Wonderful. Now, I must admit that I'm a bit curious now. Maybe we could have shortened this proof just as we shortened some of the other proofs.
So we definitely could not have shortened to the extent of not writing anything.
That's right,
because
that
we
didn't
did
work.
try and didn't work. But could we perhaps have skipped some of the steps?
Let's try it. So in the theorem, let me just erase some of these steps and see where we end up. So if I erase, I'll keep this assertion, which is a property about the right unit of concatenation. But let me erase all of the rest of it, including those recursive calls, and see if Daphne can apply them. That was apparently a little bit too much, or that was not the recursive call. We do, of course, need still to call the lemma. Daphne does not invent lemma calls for us.
Of course, yes. After all, the discovery of the lemma was a major step in our thinking.
That's
so,
right.
Yeah.
But with that,
That's
then it's happy.
So that's a shorter proof.
Let's try something similar for the lemma. So let me be optimistic again and just erase a few of these things. I'll keep the assertion about associativity, because that's something that Daphne did not discover by itself before. Here we do have the recursive call, and I know that Daphne can call, if it just has an idea of what it should imply the induction hypothesis to, it often does not need the call explicitly. So let's see if we can get rid of that. I'll keep the other assertion here too, though, about the associativity. And we had the third case where we needed associativity, so I'll keep that one as well. But let's erase the rest and see what happens. And indeed, it seems Daphne proved that as well. So here's a shorter proof of the same thing.
Right.
What do
Yeah,
you
that's
think of that?
interesting. Well, I think it's interesting because usually when, as a mathematician, you write a proof, the point at which you apply the inductive hypothesis is an important point, and you want to record it. And here, it does not appear anymore. On the other hand, as a mathematician, you quite often say, by induction and application of lemma so-and-so and lemma so-and-so. And that is the flavor of this proof.
Excellent.
So we see that there are many different flavors of proofs that you can do in Daphne.
And we can have them, write them in which style we'd like. We can start off with the more detailed one, and if we don't care about the steps, we can delete them, or of course we can always keep them. I think this is so beautiful. We should sit back and just admire it for a while. What do you think?
Yes, I think we deserve, and Daphne deserves some admiration now.
Good. All right, so in this episode of Verification Corner, we took a look at a program that encodes and decodes trees in a particular way, and we proved the correctness of that. And in proving that, we needed to include some other mathematical lemmas, and those mathematical lemmas we did with inductions and calculations, which we did in the program verifier. You've watched Verification Corner. I'm Rustan Leino.
I'm Sophia Drossopoulou.
Program safely.
And prove safely.
Verification Corner!